Welcome everyone, and there's a few people still trickling in. This is, of course, our third, sadly, and final session of the Wonders of Colorado's Glacial Landscape, our spring 2024 Right Ed semester. So before we get started, I would like to extend some thank yous that are overdue. The first thank you is to the anonymous donor who is underwriting this course for everyone and allowing folks to be able to join for free this wonderful content. It's fantastic, and we I think have a new record. I believe we've got 96 participants. So wow, that's huge. That's
Wow.
awesome. I know.
Good.
Yay, that's
Yeah.
fantastic. So thank you so much to that anonymous donor. And then, of course, a huge thank you to Vince. He's put together such fantastic material for us. My, brain is spinning over all this content, and Dee put it very well. Hiking is ruined now because we have to look around at all these rocks and think about what we're seeing. So thank you so much, Vince. You've put a lot of time and effort into this, and we really, truly appreciate it. I'd also like to thank Dee and Larry for all of their work in the Right Ed course and putting these semesters together. It's fantastic. I can't wait to see what's coming next. We will, of course, keep everyone posted. And lastly, I just want to thank everybody for joining. Thank you so much to you guys. You joining these classes supports the Right Opera House. We're a nonprofit, and we really appreciate your support. So thank you so much. I'm just going to remind everyone that
Kate, sorry, can you hear me,
I'm
Kate?
going to be muting folks.
Can
I
you hear me,
can.
Kate? You missed one thank you,
I
and that's to
can.
you for being the host for all of this and doing such an excellent job keeping it all on track.
I agree, Larry. Thank you, Kate.
Oh, well, it's my pleasure. Oh, I can't thank myself. That's so silly. Well,
No.
thank you. I appreciate that. Um, well, I do want to just remind folks before we get started that the chat function is fantastic. Use chat function if you have questions about the content that we will review at breaks or when convenient, and especially at the end. And I will, once I turn things over to Vince, I will go ahead and mute everybody to make sure that Vince has a seamless and uninterrupted presentation. And gosh, one more thing I wanted to say, and that is there was a handout from Vince pertaining to today's lecture that a couple people did not receive because it was a large file and their email wouldn't accept it. And so I've since Vince sent a smaller file, and I've since resent that to those folks. And it was also had the recording of last week's lecture. So hopefully everyone's seen it now. Just look in your email inboxes. It would have been earlier today. So sorry for those folks who weren't able to get that in time. It was just a big file, and your emails said no thank you. Anyway, I will, without further ado, for the last time, Vince Matthews.
Want to mention, and that is that even though this was underwritten, the cost of this, normally people have to pay for these courses, and the whole purpose of this is to raise money for the Wright Opera House. I visited the Opera House in the 70s to watch a wonderful movie on the San Juans, and so is there a way that folks, even though they got in free, could make a donation to the Opera House?
Wow, that's very thoughtful of you, Vince. Yes, of course. If you visit our website, which is thewrightoperahouse.org, there is a lovely donation button there, but also a button that you could subscribe to our weekly emails that are really helpful to talk about things that are coming up, might be of interest to you. Lots of information on there in addition to donating. So thank you so much for that, Vince. That's very kind.
Okay. And thank you for sponsoring this. Okay, well, let's get rolling then. Just finishing up a few things from last time and some questions that people emailed me about. There was a discussion about thrust faulting, and here you can see thrust faulting of the sediments as a glacier advances down here. And there are even models with thrust faulting in the glacial ice itself. There's debate about this thrust faulting, what it really is in the ice, and some people say it's just trains of air bubbles that are coming to the surface, and it's not really thrust faulting as one thinks of thrust faulting, but that's so far in the weeds. I'm not even interested in going there. Anyway, so Luke asked a question about Uncompahgre Peak. Did it have glaciers? He didn't know, but it's high enough for snow. Well, Uncompahgre Peak's about probably 12 to 15 miles east of Ouray, and it certainly had glaciers around it. Although when you look at it, it's kind of interesting because it isn't easy to always find clear evidences. For instance, here's a big area that's kind of like a cirque, but there's not really a high wall on this side. There's a pretty good high wall there. There's a pretty good high wall there, but it's not really much of a bowl-shaped area. Same kind of thing, sort of diffuse looking bowl-shaped areas here. You can see on this side over here that it's just kind of a smooth area down, nothing really cirque-like. This is kind of cirque-like on this flank of it. And this side is not really much of a cirque in here. There's not containment on either side, although there's a big head wall. And if we look down this valley right here, we can see this clearly a beautiful U-shaped valley, and it's coming away from Uncompahgre Peak. And the reason that these things are not as clear as you'd like to have them is there was so much ice. Uncompahgre Peak is right here, and the area was practically covered with ice, with exception of the little peak sticking up that's well on its way to becoming a good-looking horn, just like the spectacular horn that we saw over here at Wetterhorn Peak and Little Matterhorn Peak here. So there's our Uncompahgre Peak, and we had ice glaciers flowing away in this direction here from these sides of it. And we had ice flowing in this direction and flowing in this direction. And it was basically just stranded here in the middle of this little ice field up here. And the reason that you don't have containment in some areas is because you had coals eating away at the thing in between. So moving to the Front Range, Steve asked, why didn't the Bear Creek Glacier, outlined in yellow, make it below 9,200 feet? So this is Mount Blue Sky right over here, and this is the glacier that Steve was asking about, and this is the area at 9,200 feet. And the smart aleck answer to this is not enough ice to make it further than that. And let's just take a look at that for a second. Here are several little cirques that fed down into this. But if we look around Mount Blue Sky here, we have a glacier that's coming around here, some of it spilling over in this direction, and it's going down here, and some of it's spilling over in this direction, and it's heading down this direction. And from the other side of Mount Blue Sky are these glaciers going off here, but this is the cirque. Remember that we looked at the arête in between Mount Bierstadt here and Mount Blue Sky over here, and this glacier is going and joining this glacier here. And there are glaciers coming in from the side here, from other directions farther west. Another one's entering here before it gets to Georgetown. So there's ice constantly feeding in here from other sources. And if we look down on, sorry about the fuzziness here, but this is Idaho Springs here, and this is Dumont. We're up here, this is Guanella Pass, and these glaciers are coming from Mount Blue Sky and Mount Bierstadt over here. They're coming down and getting ice fed in here and fed in here to Georgetown from all of this area up here at near Eisenhower Tunnel, Loveland Pass, and Gray's Peak and Torrey's Peak. They're all sending their glaciers down here to Georgetown to join in. And as the glacier goes on down, it gets ice from up in this area, and it gets ice from this huge source area from Berthoud Pass around over to Red Mountain and other areas like that. So that's why this one got down to And it didn't get down anywhere near the Animas Glacier, which got down to 6,500 feet or so. This one got down to 8,200 feet, 1,000 feet lower than that Bear Creek Glacier. So again, the smart aleck answer and the detail answer is not enough ice to get that glacier down below 9,200 feet. This is a little exercise I did. It was kind of fun. The question is often, how thick was the ice in this valley? And we have lots of things that we've talked about. We've got the truncated spurs that tell you the minimum thickness that you have. You have hanging valleys that tell you the minimum thickness that you have. You have sculpting of the valley walls, which tell you the minimum thickness that you had of the glacial ice. And we have moraines that tell us about the minimum thickness of the ice where the moraines are being deposited. So this was an interesting little thing. I thought the ice was about this high just from looking at the features back in the valley of Lake Creek. But I decided to do a little experiment because this is a nice place, I think, to do that. And this is the width that we were just looking at back in the bedrock valley. But as the glacier came out of that constraining bedrock valley, it's expanded and thinned. So it spread out and it thinned. Well, eventually, down here, it's much, much wider than it was there. Right here, the ice was a minimum 600 feet thick. If we go back in, and then as it receded, it became even narrower and thinner. So what I did was to take the right where it comes out of the valley, where it begins to spread out, and this is a topographic profile across there, from moraine to moraine. And the moraines are 1,000 feet above the present valley floor. So that meant the ice was at least that high. And so what I did was to take this 1,000 feet there, and I went in and I counted by hand. I put little squares on here that represented square feet, and actually more than square feet, a little bit larger than that, because what I calculated was that the area of this glacier was 12 million square feet from moraine to moraine if you took a slice down through it. And so I thought, what would happen if we put 12 million square feet back into that valley that's much, much narrower? How much would that force the glacier up? And so there's 12 million square feet back in that bedrock valley. And all of these are at the same scale, so you can get a good feel for what it's all like. And the answer is here from this little exercise, 2,200 feet of ice. And in some places, it's actually 2,400 feet thick. So I tried this on some people who had worked in this valley. Does this give you a heartburn that this number of 2,400 or 2,200 feet of ice is too thick? Well, one guy said, it's way too thick because I said there's only 1,500 feet of ice in there. Well, the other two people were kind of interesting. One guy had a model for glacier thickness and movement and all this sort of thing. And he actually went in and studied this and did some modeling of what would happen. And he said, I think it's kind of high. I don't think it's really quite that high, but the models, the far end of the model actually agrees with that much ice. I kind of like a more medium, he said. And the other one had already modeled this area, and he looked at it and he said, it's a reasonable number. So anyway, there's three experts looking at this little game I played. Now, doing just square footage is not valid because you're talking about volumes, and you also have the glacier is actually moving, so the speed of the glacier comes into this. So, but anyway, that's one little exercise that I went through I thought you might find interesting. Okay, well, we were talking about rock glaciers last time, and we were just getting to this point below Pyramid Peak, which is right across the valley from the Maroon Bells. And this had a fantastic thing that a person from Ouray really was responsible for documenting what happened here, one of the incredible hikers down there, Rick Trujillo. And this little area right here, I'm going to blow up, and you see this little crater here. This is a 2011 view on Google Earth. And let's take a look at some. This is a 1997 shot by Rick. And what happened was there was suddenly this collapse, this crater that formed in the rock glacier, and there was water in the bottom of it. And that really was an astounding thing just in itself. But Rick went back, and in 2002, this was what that crater was showing. And you can see the people here for scale. This is a huge, huge block of solid ice below this thin little cap of rock on top of it. So this, people who want to make these things, rock glaciers being just covering old glaciers, this was strong evidence, although a lot of people didn't really know about this. So by 2011, that was 2002 shot. By 2011, that had all closed back up and people can't go back up and study it scientifically anymore. Okay, so that was one piece of evidence that supported solid ice. The question is, how fast do these flow? And they flow at a lot of different rates. This is a really nice one up above Breckenridge in the Spruce Creek Gulch. And it's been studied very detailed by students and faculty at Colorado College. And it's moving at about 3 inches per year, very slow, but they have lots of places on the glacier. And so they understand how it's flowing. And it clearly shows that the central part of the rock glacier is moving faster than the outer parts. And of course, then we have this wonderful Imogene glacier up toward Imogene Pass out from Ouray. And I've got 1 foot per year, but I need to update that. It's actually 2 feet per year that this is moving because of the painted rocks that were put across there in the 1970s. This is the Maroon Bells rock glacier that we can see from the viewing point, but most people don't really notice, and it's flowing down at 2 feet per year. This was documented by the USGS back in the 1960s. And then there's Mount Sopris, which is just south of Carbondale, quite a ways south of Glenwood Springs. But the next time you look up there, look for these rock glaciers coming off there because they're very spectacular. And this one is moving at about 3 feet per year. So you get lots of different velocities that occur on these things, but the point is they're still moving. Okay, so remember we have these models here of ice core, which the Pyramid Rock Glacier seems to do. And we're going to see an example here of interstitial ice in a little bit when we talk about permafrost. Missing a slide there, but you've seen it already of the Hurricane Basin Rock Glacier. I think I stuck it later on, just right before we started. Okay, so I want to look at periglacial features now. These are features that are there as a result of cold temperatures, and rock glaciers are periglacial features. They're there, exist, and they move because it's cold up there. And they mostly occur above about 12,000 feet. Most of the rock glaciers are up there in the really cold territory. Okay, so this Niwot Ridge Research Station is kind of interesting. It's located 12,264 feet above sea level. The whole station isn't, but part of the area. This was put up by University of Colorado. It's now an international research station for alpine research. And this shows the average daily this is taken from the average daily temperature that was recorded from 1952 to 2019. And so it's a really, and actually this average annual temperature is what's shown here in the red because it smooths out some of the wild swings that you get on a daily temperature chart. But what you see is that it's pretty uniform in temperature through the years. And the main thing is that the average is 3.5 degrees centigrade, minus 3.5 degrees centigrade, or 25.7 degrees Fahrenheit. So it's quite a bit below freezing. And that average for this whole length of time, about 70 years, is consistent with permafrost could exist there, because permafrost definition is that you have 0 degrees centigrade average annual temperature and ice staying in the ground for more than 2 years. So permafrost is this zone right down here where the ice never melts and it stays permanently, as the perma implies. But above that is an active layer. And this, the active layer is an area on top of the permafrost that melts in the summertime, and then it refreezes in the winter. The permafrost below doesn't do that, but that active layer does. And this is where the action for most of the paraglacial features that we see decorating the landscape in Colorado and in other places, this is where the action really is. It's properly named the active layer because that's where the action is. And so we'll take a look at some of the things that result from that active layer freezing and melting and freezing and melting and freezing and melting year after year after year. This is a part of a little poem that Hazel Cox wrote about stone fences stretch in ordered rows, abandoned grass-grown plots enclose. The saying was that every field in this new land 2 crops would yield. Potatoes would in summer grow, and frost-heaved rocks in winter snow. Man, beast, and fowl must all be fed, and so the crude and homemade sled, a clumsy stone boat, was brought out by patient oxen, dragged about until once more the field was cleared, and higher yet the fences reared. So they actually had these stone sleds that farmers used throughout the northern area in Wisconsin and northern New York and other areas, because every spring there'd be new boulders that appeared in the fields because the frost action had heaved them up, and they had to be cleared before they could farm. Okay, so here's an area on Trail Ridge Road of the tundra, and we call it the frozen tundra because it's over permafrost supposedly, and there have been studies along Trail Ridge Road that suggest that there's permafrost underneath this, although some of those have been questioned, and the whole idea of where do we have permafrost, how much permafrost do we have, is kind of a question right now. And there was just a recent paper written in like 2019 or 2020 that sort of outlined the problems of having permafrost in Colorado. I think part of the problem is that permafrost really forms well in deposits that have interstitial pore space. So the ice of the permafrost can form in between the fragments. This is solid bedrock here up on Trail Ridge Road. These are granites and metamorphic rocks, and they're not deposits. They get broken up on the very upper surface, but they don't have the porosity and all to develop permafrost like you'd like to see. Okay, so we talked about, going to talk again about rock glaciers because we're talking about permafrost. And there's something really fascinating, I think, about this. And it's in the Climax molybdenum mine up at Fremont Pass. This is the world's largest molybdenum deposit. And in this view that we see, there is a rock glacier right there flowing essentially I got some technical people would say, well, you know, rock glaciers are really on the floors of cirques, and that one's on a steep cliff coming down. Well, whether it's a rock glacier or not, it has the features of rock glaciers, and it illustrates a very, very important point. This is an ore pile. Now, for those of you that don't know the history of this, the Climax mine shut down in 1983. It turned Leadville essentially into a ghost town. You could buy a house in Leadville in 1990 for practically nothing. And lots of people, some of them bought lots of houses, and now they're making a lot of money from renting them out. But they had been mining up here at 12,500 foot level, and they were storing the ore that they had been mining on this pile right here. And so this is a pile of ore that has been mined. So it's loose rock that needs to be taken, or was waiting to be taken down here to the processing unit to grind it up more, and then run it through their processing mill and ship it off. So when they shut down, this thing was up at the top surface, and it went all the way across to here. So that's where the pile was that they had been mining up there when they shut down. Well, you notice that it's not here anymore. It used to go over like this, but now this part is missing. And where did it go? It flowed down into the pit. It flowed a half mile horizontally, and it flowed 1,000 feet down. And look at the shape that you see right down here. Now that you're rock glacier experts, you can see that this has got the same features as your imaging glacier. And this was all interstitial ice. This is all that's left of it today. They've been mining through it. So they know that it was interstitial solid ice that was what the thing was made up of rock and ice. And this is what it looks like from above, and you can see it looks just like all the other rock glaciers that we've been seeing. It has a levee at one of the points of the arrow and the furrowed ridges in the interior. I think the important thing that we know here is that this was loose rock. We know when it was put there, and we know that permafrost developed in it within 20 or 30 years, and that eventually it began flowing as a rock glacier, or like a rock glacier. So it is currently still moving at about 1.5 feet per year. What's left, it moved more rapidly than that before they started taking it away, and they mined it away as they opened the mine back up in 2012. Okay, so here's about 8 miles east of Ouray, the Hurricane Rock Glacier, and remember they drilled an adit through here, and rather than solving the mystery, this adit drift just added to it, because you had the interstitial ice like we see at Climax, and clean ice like we see at Pyramid Peak before it went into bedrock. So there's lots more interest in this, and I'm having kind of a friendly little debate with one of the professors who's interested in this at the University of Colorado, and he'll say, well, what about this exposure of clean ice? And I said, don't forget Climax. He said, oh yes, Climax. So at any rate, it'd be interesting to see if we ever resolve this. Ice wedges is a paraglacial feature, and they're kind of interesting. This is up on Herschel Island on the coast of the Arctic Ocean in Canada, and you can see that there is a wedge of ice extending down through here. This is permafrost. And notice on the sides what's happening to these layers. They've been bent up on both sides next to that wedge. So we get ice that bows this stuff up. You get a wedge forming something like this. And when the permafrost melts, if it ever does, you get it filling with sand. So you have an ice wedge sand cast. And you notice that the layering in this ice wedge sand case is vertical. It's not horizontal like it should be, or like we think it should be. It's vertical. And I think the process there is that as the ice wedge begins to melt, it'll melt in the summertime, and along the edges, it'll get it'll develop gaps, and the sediment falls down in there. And then in the winter, when it freezes back again, it pushes against that, and it creates a little layer, and then it melts in the next summer, and another stuff falls in, and then it expands and packs it as it expands. And eventually, when it's completely gone, you end up with this little layering that's parallel to the walls instead of being horizontal. And here's an example in Colorado, out on the eastern plains, that this is a wedge. This is an ice wedge sand cast right here. And the layers are parallel to the walls. They're not horizontal. And notice how these have turned up against this ice wedge sand cast, just like up here on the edge of the Arctic Ocean. And these things in 3 dimensions form polygonal patterns. Okay, so the Colorado Geological Survey was doing an investigation out here in the possibility of a fault, and dug trenches that were about 15 feet deep. You can see that they are benched for safety to keep them from falling in on the people working there. This is a common thing. You have to lay these back in order to make them safe. And so we got kind of a 3-dimensional exposure there. Skipped ahead a bit, but here's a polygonal pattern that was exposed by a road grader on the surface. This is about 40 miles away from that trench. The point of showing these is that, these were widespread out on the eastern plains. And this is 90 miles east of Denver. It's the southernmost discovery of permafrost. And in this trench, this is a diagram of the trench that was drilled. There are ice wedge sand casts of 3 different ages. Okay. The yellow are Pinedale. The kind of light tan are early Wisconsin age, and Bull Lake are these darker wedges. So we have evidence out on the plains of permafrost on the plains during all 3 of these potential ice ages that we've been looking at. And this is about 6,000 feet lower than what permafrost can form today in Colorado. So it gives you some idea of how dramatically cold it was during those days. And so this is out on the plains at 4,000 feet. Think about 5,000 feet in Denver. That means that you could have had permafrost anywhere in Denver that it had the place that you could form it. And there are people beginning to think about the implications of this, particularly as it relates to the area just north of where Colorado Geological Survey was doing their scientific trench. And the geologists followed this for about 25 miles, looking to see what they could see in the open trench. And all of those yellow arrows are pointing to ice wedge sandcasts. So there were hundreds of them out here in this trench that were exposed. There were over 100 in our trench that were mapped, and many of them were dated. Okay, so enough of that. Let's go on to sorted stone. These are things that just they blow my mind every time I see them. I just think they're incredibly exciting. These are on Prospect Mountain, which is just east of Leadville. This is the road up to Mosquito Pass, and this is up on top of Prospect Mountains where very few people go. And you can see these polygons that are surrounded by large fragments of rock. And when you look down into those large fragments, you can't see a particle, a small particle anywhere in them. They're just completely sorted. They're called sorted stone polygons, S-O-R-T-E-D, not S-O-R-D-I-D. Okay, so patterned ground. This is what it looks like up close. And in the center is fairly fine-grained material. There'll be an odd rock, larger rock there. But surrounding these centers are these huge rocks that many of which are turned right up on end. I mean, they're vertical. And it's just mind-blowing to look at this stuff to me. And how do they form? I bet you're thinking that question. How does this form? Well, I'm not going to tell you because I don't know. One wag said that he had read papers, all the papers that he could get on the origin of sorted stone polygons. And there were 34 different models for forming them. So I'm not going to tell you how they form. Clearly, frost action in the active layer has a major problem, a major role in doing this. But how exactly it does it is hard to get. This is up in Rocky Mountain National Park. Notice that. This is just above the lava cliffs. If you're ever looking for a little short hike up to the top there, you can look at these and you can see from the road sorted stone stripes. Here is a Jeep down here with the two geologists operating the drone, and you can see this top of Prospect Mountain, how extensive this cover is, and it's actually about twice that size. Okay, so one of the things that's neat about this is that it's relatively flat up on top of Prospect Mountain. There's a very slight slope. And you notice how these polygons, they're starting to stretch into stripes. See how long that is? And these are not moving downhill. This isn't steep enough to move this stuff downhill. It's just that on the slopes, they form the stripes when the frost action goes to town, like it makes the polygons up on top where it's flat. So you can see these long stripes beginning to develop. And when you're driving along Trail Ridge Road, if you look up, here are sorted stone stripes that are part of patterned ground. You go up on top, then you can see the polygons. And this was sent by one of the people who took one of my classes here, and this is really exciting that he found this up in the Sawatch Range and sent me the picture, which is great. I've got my email address at the end. If anybody does make similar discoveries and wants to send them to me, I'd love to see them. So here are stone polygons and some stripes underneath water. And during the winter, everything freezes and then melts in the summertime, and you have a lake there instead of a solid ice block sitting there. And the water, I think, illustrates that incredible sorting of size of the rocks versus the sand and gravel that's in the middle of this thing. Okay, tors. Tors are things that stick up above the rounded surfaces in alpine areas in Colorado and the rest of the world. Scotland's famous for tors. And their origin is not particularly known, but they're interesting. And this same guy that I'm having the discussion with about rock glaciers proposed that there are things associated with these features that could only occur by lightning. And that's when I first became tuned into lightning as a potential geologic agent. And since I've found many examples of that that are really quite exciting. And I think it's a totally underappreciated geologic process. But at any rate, they exist. And this is in Rocky Mountain Park on the trail up to Long's Peak. And this is a view of the trail ridge up here. And you can see a number of tors sticking up over there. And they're thought to be, they form in the paraglacial environment, not really clear how. This whole area over here is covered with solifluction lobes. Okay, so block fields. They don't have the patterns that you see in sorted stone polygons or anything like that. They're just fields of broken rock where a lot of rocks are up on end, and they're attributed to frost action. Here's some in the Mummy Range. This is on the boulder field going up to Long's Peak. This is along Trail Ridge Road. You can see these things just standing up on end. Absolutely amazing. And Park Service doesn't hire people to go around and do this. Okay, the solifluction lobes that I just sort of glanced over before, they are things that are moving down slopes in lobes, and they move episodically annually. So what happens is that in the active zone, in the wintertime, you freeze. When you freeze, the ice expands and the ice pushes material up from below. In the summertime, the ice melts and you get this goopy mess that flows down the hill as a lobe. Not far, but year after year after year, it does. And so here's looking at the same area that we were looking at from down below before when we were looking at the tors. Here's that surface of lobes that have been flowing down the hill year after year after year. And so what happens is these things in the wintertime, the ice pushes the lobe up. Then in the summertime, when it melts and becomes a goopy mess, it just slowly slides downhill. Then when it freezes again, moves up, and then it melts and it slides downhill. This is looking end on up at Rollins Pass at solifluction lobes, and you can see that there are a lot of coarse material in them. Trail Ridge Road is a great place to observe them, and you'll see pretty much identical image that you see there. Here is one of those things that has been risen up. Here's the toe kind of that's been risen up during the winter time, and it hasn't quite, the ice hasn't quite melted in it and started to flow and become the goopy mess. It's still a pretty rigid collection of soil in there. This is one over south of Keystone. See these lobes coming down here. And these, this surface over here is covered with them too. It's just the lighting isn't such to accent them. Well, we have some other paraglacial features in here called mounds. And they're sort of interesting. This is a LiDAR image south of Twin Lakes. And it shows all these little round areas here. And this is what they look like on the ground. Not much to write home about. Between the white arrows is one of these mounds. There are lots of others. There's one out there. There's another one out here. They're all out here, but you'd walk right over them, never pay any attention to them if you hadn't seen the pattern of them on the LiDAR. And what we see here is a couple of things. They are a foot or so, maybe 2 feet higher than the surrounding area. And as you walk over them and you look at them, the grain size in here is quite a bit coarser than it is out here. This is all really fine sand and silt out in here, and these are little pebbles and coarse sand grains in here, and sometimes a cobble or two that'll occur in here. So this is much more receptive to the plant's roots. It gives them the ability to go deeper, and so the sage grows much more robustly over these mounds than it does off the mounds. And this is an accented LiDAR image that Steve Camella did for me that's just really dramatically illustrates these things. And you can see that there are hundreds of them in this picture. And this is pointing to the one that I was showing on the ground. And this is the location of where that vehicle was in the background. So here and there. And here it is on the LiDAR. Okay, and we have craters also that are paraglacial features. And here's one right here. And this is down north of the sand dunes in an area of old dunes. And that's a pretty spectacular crater. And a lot of people thought that's got to be a meteorite impact crater. In fact, there are lots of little craters out here. And so people were really thinking that there was kind of a meteorite fall in here, that there's a field of craters that were developed from this. And you can see the beautiful crater right here on the LiDAR. And there are other craters of different sort of ages or generations all around here on this sand base. Well, there was a team of scientists that went down there to study these, and you can see they cover a larger area. There's our, there's our beautiful one right here, and there are craters all the way back. There's one that's rather diffuse over here. There's one that's been eroded by a stream coming down over here. There's here. They're just all over the place. And so this team of scientists did studies over them. They ran geophysical instruments over them and mapped them and studied them. And they concluded that they were kind of these pingos that form on the north slope, and that they, with time, collapse and have maybe little lakes in them, but now are just craters. And I can't validate one way or the other whether that's true. Okay, so want to quickly look again, because we're going to move from periglacial to paraglacial. And before the glaciers came to Colorado, the landscape was pretty happy. It was pretty stable gravitationally. The streams had created stable slopes back here, and it was just in gravitational happy land. Not many landslides caused from it or anything like that. And then along came the glaciers. And they, remember, I want to repeat again, those glaciers oversteepened those valley walls, much more so than what they were. And they left hanging valleys up here that were going to appear. They cut these triangular facets. They really, really modified the landscape. So here we are after glaciation, and we're left with this oversteepened walls, and there are lots of things that can happen there. It's out of gravitational equilibrium, so landslides are quite common. And these streams roar down out of glacial hanging valleys and create these alluvial fans at the bottom of the rushing streams when they slow down, lose their speed, and drop out. And you have lots of little lakes that form up in the U-shaped valleys and the cirques. So let's look at some of those. Well, talus is kind of the first sort of thing, and this would be a talus apron here east of Leadville in this nice little cirque that's got rock glaciers, and up above is Prospect Mountain with its patterned ground. So you can see these talus cones, and one of the things I want to point out is notice that there's a stream valley down here, and there's a stream valley down here, and there are levees in this stream valley. These things are supposed, in the textbooks, they're supposed to form from rock fall. And certainly there's going to be lots of rocks up here that get loosened. And every winter you're going to have water that gets in cracks. And when it freezes, it's going to wedge boulders loose and they're going to fall down and roll down. But I think most of what builds these cones, personally, I think is streams coming down, because every one of these, the peaks of the cones all are at the base of a deep erosional gully, every one of them. And I think that probably the dominant mechanism for deposition of these things is water, not gravity, but that's just my opinion. So this is the classic idea of how they form, is that rocks break loose up above, they bounce down, roll down, they accumulate at the bottom. And what you're trying to do is make this more stable. You're trying to make this more stable. It's oversteepened here, and you can see this slope is slightly less than that. So it's working to do that, and it's eroding back here. So the whole goal is to get a slope eventually that's in gravitational equilibrium. This is what these things look like up close. This is on Mount Sherman, near Leadville. This is these are vegetated cones, sort of stabilized on the $1 Million Highway between Silverton and Ouray, and pretty dramatic and high cones. Okay, so I mentioned alluvial fans, but let's kind of look at them a little bit closer. I was walking my dog in my neighborhood, and the area that I live in before man screwed around with it is nice, gentle, rolling hills, just one right after the other. But now there's a housing development that's been built here in the time that we've lived here. And in order to build that housing development, they had to cut roads in there, and they cut into this slope and to make the road. And so they oversteepened this wall. And of course, as soon as they put the sod in up here, the first rain that came along eroded down this way, a little gully, and eroded a deep gully here. And when it reached the bottom, it created this beautiful little alluvial fan. And that's what happens in our post-glacial world, just on a larger scale. There's the original slope above that, and you can see they've oversteepened it here. Well, here's the same thing on the road up to Independence Pass. We have a hanging valley up here. Here's our main U-shaped valley, oversteepened valley wall, gentle gradient. Streams come down, they hit that lip, and they roar down that oversteepened wall, and they erode deep gullies, and they pick up lots of material. And all of a sudden, then they lose their velocity at the bottom, and they build this alluvial fan like this. Here's another one along the same road that is really, I think, wonderfully interesting. You can see the bracket shows where the deep gully was, and then you can see the fan spreading out here. There's that fan looking from up above on the road to Independence Pass. You're nearly there where you can get this view. And you notice that it went across the valley, and it dammed the valley, and it stopped it created a lake and backed up the lake, North Fork of the Lake Creek, and formed a lake. And then the lake sedimented in, and what we're left with today is a boggy, swampy area with a meandering stream across it, just like what we saw at Durango from the moraine damming the Animas River. Here we've got an alluvial fan damming the Lake Creek. And anytime you see these areas in the mountains, be suspicious that something dammed this and altered it and created a flat floored area that's boggy and has meandering stream over. Because the stream right below it, once it cuts through the alluvial fan here, it's much straighter downstream, like it should be in a mountainous area. landslides. They're another feature that we find in post-glacial areas because of steepened walls. And I see by the time, why don't we take a 10-minute break and we'll come back and look into that.
That sounds perfect. And we're right on time as always. It is, let's see, it's 10:57 where I am, but minus 2 hours. That means it's, I'm so bad. 10 o'clock. No, 11 o'clock. Please, no one make fun of me. Anyway, so we will reconvene at 11:10. We'll call it 11:10 just to keep things even.
Oh, okay.
And make.
See you then.
We do have a couple questions on chat, Vince, if you wanted to address those before
Sure.
or as we come back from.
We can do it now.
Yeah,
Okay. Well, oh, go ahead.
so I had a question. This is Jennifer Cram. Back when you were talking about the sand casts and
The ice wedge sand casts.
and when I was just looking at the cross section there, the layers on the side, it didn't make sense to me intuitively the way they were bending, like they were bending up, like the ice came up, and I thought it came down. If you have that picture that showed the spear of ice going down, and then you had the layers on the side were bending up on either side of it. Intuitively, it seemed to me like they would bend down.
Oh, I think I understand what's puzzling, and I think intuitively you're correct. And I don't know that I will have an answer because,
Yeah,
yeah, I think it's as the wedge grows in volume that it's growing. I mean, the way I think about it is that it starts as a little thing and it expands with growth, and the ice expands and it warps up the layers as it expands outward. That's the way I view it.
okay, that makes sense.
But I'm not an expert on this, so I know what you're saying.
Yeah, no, that makes sense. Thanks.
Okay. Because that's the same thing as when it's, how you develop the vertical layering parallel to the walls, expanding outward, packing it. But they're pretty impressive, regardless of how they form.
Vince, can you hear me?
Sure.
Your LiDAR enhanced photo of what you refer to as mounds showed a suggestion of a parallelism to that one, sort of a parallelism to some of those mounds that looks like it's parallel to a little bit of a from lower left to upper right change in relief or ridges.
Well, there
any
are ridges.
comments?
Yeah, there are slight
Yeah,
ridges
okay.
in there. And if you're only talking about, this is a ridge, this is a little swale, this is
Yeah.
a swale between the ridge here. So here's one kind of at the bottom of a little low area, but these are very, very low relief. I mean, because you're expanding things, you're also expanding all of it. No, I was going to say, Lou, I thought you were talking about, it looks like there's a row of them here and a row of them there. And then you can say, okay, there's a row of them here and
Maybe
a row of them up there. And it reminded me of the old axiom that you can draw a straight line between any two mines in South Arizona.
Remind me what was the black arrow indicated?
That was that was this, and the star is the vehicle in the background. So that was just the black arrow was pointing to this.
Oh, okay, gotcha, gotcha. Thank you. Vince, are you still there?
Yeah,
In the photos that where you shared the interesting features of a rock glacier, I believe it was around Uray, where a while ago it was observed there was a collapse. Even prior to that, it was recognized that you could see some of the ice that underlay that. Do you recall that? What I'm talking about?
yeah. Well, the one that I'm thinking about that I showed is the cirque between the maroon bells. Excuse me.
Okay, all right.
It's across the valley at Pyramid Peak.
And for which a photo from a number of years back had shown, had exposed some of the underlying very well stratified ice.
You're breaking up, Lou. I couldn't catch that.
Is that photo?
Well, there's a
Can you
photo.
hear me now?
There's a photo in Messages in Stone that was published back in 2003 of that exposure of ice. And that was given to me by Bruce Bryant, but he didn't tell me who actually took it. And it was actually Rick Trujillo that took it and gave it to Bruce. And then I got it. And then Rick gave me the rest of the sequence there where that showed the water that developed before the ice was exposed, or the large exposure of ice. Is that what you're asking?
Well, my question was, how do you count for the very well stratified ice there? What is defining the stratification in that ice?
I'd first of all say that virtually anybody who looks at that would say that's glacial ice, because glacial ice commonly has those layers in it, and those layers can get deformed. They are thought to form from annual accumulation that then gets covered with snow, and so fine material, silt and sand kinds of things, and occasionally you'll have boulders on that. So they're almost like annual rings.
Gotcha. Thank you.
Annual layers, yeah. So I'm disappointed to see that, because I don't think you can explain all these rock glaciers that they're covered glaciers. I think there are real problems with doing that, but it's there and it's real, and they're an amazing enigma, I think. Okay, well, it's 10 after. Let's get started on landslides. And okay, so here's a beautiful U-shaped valley, oversteepened walls. Have you ever heard that before? And this lake down here is the largest man-made lake, natural lake in Colorado. And it's caused by a landslide that came out of this area up here, came down and dammed the stream. So this is looking back, here's that lake, and this material right here slid down and created a landslide deposit down here that was about 300 feet high. And you can see that the stream has started to cut through that and has not made very much progress. Part of the Pinedale Moraine up here, which is 600 feet above the lake level, still to it. And so here's a large landslide that has occurred within the morainal material. So bedrock can fail and moraines can fail in huge landslides. This is Vail, and the Vail Valley here in East Vail. This is looking toward the south. It's an oversteepened glacial valley wall. This is the place where people go to ski to die. And it's a very, very dangerous area to ski in. The guys that came back from World War II, from the 10th Mountain Division, and decided they'd like to start some ski areas, learned something over there that was very, very important. And that was that you needed an area where it was easy for intermediate and beginner folks to get down to the base. So these are pretty intermediate slopes back up in this area. And, but if beginners had to come down this, there was going to be a mass death sort of thing. But they found a place that had paraglacial material. This is a huge landslide. And landslides are designed just like the talus cones to put those things, the slopes, back on lower slopes so that they'll be in gravitational equilibrium. So this is the area that they chose for Vail, and it was very good because you can take the Lazy Day green trail down or the blue. And I remember I started at one time and suddenly I see the trails dividing in two right in front of me, and both of them are black, which was not what I was looking for. Okay, so here's another area at Vail, what was done. You notice that there's this bridge here in East Vail as you come down from Vail Pass, but there's no stream under it. So why did they put a stream, I mean a bridge there, when there's no stream under it? Well, this stretch of highway from Vail Pass to Vail is the very first place in the United States where there actually were geological studies done before the highway was built to identify potential hazards to the highway and design the highway around those hazards to avoid or to mitigate those hazards. And that in itself is a wonderful full-day trip, just looking at all of those mitigations. This is a lateral moraine. And this is a lateral moraine up to about 1,700 feet high over here. There's bedrock extending through here, but there's moraine deposited up here about 1,700 feet above the road. And that causes rockfall because the boulders erode out and they roll down, they get up a good, and this is the elephant trap that collects them down here and prevents them from hitting private property there. So one of the things that they said was, if you cut into this moraine, you're going to have landslides for the rest of the time that this road's in existence. So they cantilevered this out away from the moraine. And that's why this bridge is here, is to get it away from the moraine so they didn't have to cut into it and have landslides constantly coming down here. Okay, the next one is ridgetop spreading, which is one of my favorite topics. You've got a glacier in a valley down here. And this is a diagram from Dave Barnes in 1989, who really, we've got him to thank for most of the things that we know about succogen. And this, when the ice goes away, as long as the ice is there, it's oversteepening the walls, but it's holding it back. When the ice goes away, there's nothing holding the walls back anymore. They're oversteepening, and they actually want to bulge out under gravitational pulls. So you get this bulging or spreading, which causes what's called ridgetop spreading by extension at the top. And the way it does this is by these little brittle normal faults. And they form uphill facing scarps most of the time. And you can have a little crustal graben downdrop block at the top. Okay, so the most famous place for this is at Bald Eagle Mountain. There's Turquoise Lake and Leadville in the background in the upper right. And this ridge runs down toward Turquoise Lake. And we know that Turquoise Lake had a glacier that came, and one of the big arms for the Turquoise Lake glacier came down Busk Creek right here. And there's a U-shaped valley, and the walls of Busk Creek were oversteepened. Okay, there's a start. At the same time, there were cirques on the other side of Bald Eagle Mountain. There were several cirques on that side. And the cirques were eating back and creating this narrow ridge that had steep margins on either side. And so it began bulging out. And there's a Sakung right there. There's another one there, another one up here. I'm standing in that one down there. And this is the yellow line is the kind of the normal slope of the area up there. And that normal slope has been displaced upward with this uphill facing little escarpment that's maybe 15 or 20 feet high. And then at the top of that, you go back to that normal slope down to the next uphill facing scarp. So there's a little fault there that I'm standing on that created the uplift of this block behind me. So Dave, who's with the USGS back in 1978, said, wonder if these things are moving today, or are they old features? So he established some permanent survey stations here and used laser surveying instrument to measure across it. He went back 10 years later and measured, and sure enough, it was moving. And with time, they changed to using very accurate GPS stations to do the measuring instead of the laser surveying. But they've been measured just about every 10 years. And I talked to Jeff Coe with the USGS in 2013 and said, 2012, I guess, and said, you know, you guys haven't been out there for 10 years. Aren't you going to take another measurement? And he said, well, if you'll help us carry the equipment up there, we'll do it. And so I and a colleague went, helped them move the equipment up there, and we did a survey, and sure enough, they're still moving. And the measurements here across that, and there are a whole bunch of fascinating things relative to this that we could talk about, but don't really have time. The main thing is that over the 38 years of measurements here, the average rate of these little uphill scarp faults have moved at about 1 to 3.6 millimeters per year. And if you say that the glacier that was in the U-shaped valley disappeared 13 or 14,000 years ago, and that then would put it unstable, and it began spreading back then the two numbers, that would give you 13 to 40 or 43 to 154 feet of spreading over that period of time, which is consistent with the height of the scarps. So it all sort of ties together that it's been going on for ever since the ice disappeared, and it's still going on because it's still unstable because there's still a steep cliff there that's gravitationally unhappy. And this is where we find all of the Sakung around the state, and the blues are areas in bedrock, and the yellows are area where the ridge that's spreading is sitting on shale. In some places because it's an intrusive that's intruded into shale, and in others it's a thrust fault that has placed bedrock on top of, well, shale is bedrock, but igneous and metamorphic rock on top of it. Then those are these right here. Okay, lakes are more paraglacial features. And this is the highest alpine lake in North America, and it's up in the Mosquito Range, and it's at about 13,000 something, although now I think some people have challenged that it's the highest, but nevertheless, it's high. And the reason it's there is because it's in a cirque that oversteepened the basin. And we also have a moraine that's adding to the capture of the water here. So here are some steps, and these steps going down, these are the Green Lakes in the Front Range, the Indian Peaks Range. And those are areas where the glacier scoured out bedrock lower than what the rock is downstream, and water backed up behind, couldn't escape easily. Here it's getting out in a sort of dribble over here, but it doesn't have any energy to really cut lower than that. And same thing down here. This is called a string of lakes or paternoster lakes, they used to refer to them in the old literature, but it's probably not allowed these days. One of the places, this is a little area over near Snowmass, and a glacier that came down this valley had a little bulge out toward the town of Snowmass, and it deposited a moraine around here, and a lake formed. And in that lake, vast numbers of animals died, probably from earthquakes triggering debris flows and their instability, and they were jostled into the lake and drowned. But the Denver Museum of Nature and Science uncovered an incredible number of things there. At our newest national monument, the Camp Hale and Continental Divide National Monument, we have a recessional moraine that dammed the Eagle River and backed up a lake about 4 miles back up into this area here. And we've actually got cores out of the bottom of the valley here and have about 250 feet of lake sediments. So we know that there was a lake here, and we know that the lake filled in with time and formed this flat floor that was so ideal to have a town of 17,000 people to train these guys who went over and did a fantastic job defeating the Nazis. So the Eagle River now is a very straight thing going through there, but the reason it's straight is because it was meandering and boggy and swampy, just like we saw in the Lake Creek earlier. But in order to use this area, they had to drain it, and so they put a straight drainage ditch through there that would channel the Eagle River and drain all of the swamps. And the rest is history, as they say. Here are the Twin Lakes. Of course, the moraines damming those and backing them up, and there still were lakes when the Hayden survey came. This is one of their sketches, and then and like they've done in so many other places, they put a natural dam in and raised the level so that the lakes are at the same level now, and are called a reservoir rather than a lake. Okay, so this is above Leadville, and I used to drive this thing all the time down to Denver because I tried to spend much time as possible in Leadville and drive down to Denver to work. And so as I drive up this valley, the Arkansas River is flowing through here. As I drive up this valley, I noticed that as I came up the hill, up the valley toward Fremont Pass, that there was just, you'd go along and the river was flat, and then it'd jump up, and then it was flat again, and then it'd jump up, and it was flat again. It was just like a set of stairs going up toward climax. And the rivers are very meandering through here. It's actually the Arkansas River, but it's not, you can jump across it. It's very early in its origin down here, up here. And so my immediate thought was, oh, those probably recessional moraines that are damming the river and building these lakes back, and these lakes are filling in, and that's why you get this little stair step sort of thing. Well, yes and no, mostly no. It's not moraines doing that. So this is a LiDAR, once again, of an area here, and there is a moraine right there. And it's very nice. If you look at it on the LiDAR, you see that it's very lumpy topography, and it's got kind of ends that point upstream, and really nice. And also, you have a little debris fan that came out of this gorge right here and covered the top of the moraine here. So you had this dam, and that backed up a lake like this. And you can see the meandering nature of the river there. Here's a little fan that came out and a landslide that came out, and they pretty well met, and they created a dam and backed up a lake here, which filled in for the next stair step up. Then there was a fan that came out of this deep little gorge and a fan that came out of this, and they hit up against this bedrock right in between them, and they created a dam, and a landslide came down and added to the whole thing and created a lake like this. So only one of these three little lakes that were created right here was created by a moraine. All of these others are those things that occurred from the oversteepening of the valley walls. Landslides coming down, debris fans coming down and forming at the base when they get down to the valley floor, and creating this series of flat-bottomed lake valleys that were filled in lakes. It's why they're flat-bottomed and they're stair-stepped up. Okay, so I thought what I'd do now is take you around the state and show you a few little places that I think are kind of neat that maybe you've seen before, but not really seen exactly like I'm going to hopefully show you. So the first one is back where we were looking before. This is St. Mary's permanent ice patch over here for orientation. And there's Berthoud Pass. Here's Eisenhower Tunnel up at the top. And there's Guanella Pass over here at the far left, upper left. And Idaho Springs down in the bottom corner. So when we leave Idaho Springs and drive up toward Eisenhower Tunnel, we're driving in this very narrow V-shaped canyon. When you look at this, I don't know anybody that would argue that a glacier came through that canyon, that it was basically carved by rivers and has all the features of a steep mountain valley carved by a river. And then we come around the corner and suddenly things just open out into this huge wide valley that's actually U-shaped. And that red circle down there is going to be showing you where these various pictures are being taken. So down on the lower left, that's where it opens up into this wide valley. And as we get up now to Dumont and look up at the little community of Dumont, behind them is a deposit of rounded boulders that's been mapped by the U.S. Geological Survey as a moraine. And we get on farther up, just past the turnoff to Empire, and look straight ahead. And what we find is this big high valley wall above us here is getting lower and lower right in here. It's a very low area just before we get to Georgetown. And that low area is an interesting area because that's where the glacier coming down from, here's Georgetown right here, the glacier coming down here carving its U-shaped valley, and this glacier coming down here and heading for Empire. These two, there was an outside bend to both of them. So they were really eroding against this ridge right here and eroded this low area in between, and the ice from one or the other spilled over into the other. I don't know which one had happened, but they basically joined through this little low area that was created. So look for that area the next time you go up there. And I'm sure that you've all seen in the Georgetown Visitor Center that there's a beautiful hanging valley coming down from Guanella Pass up above. It's got about 800 feet of above the main valley floor here, and a big U-shaped valley heading up toward Guanella Pass. And as you get closer up to Eisenhower Tunnel, you can pull off at the stop that starts with the exit that starts with a B, and I can't remember the full thing right now, but look up at Kelsey Peak here and Grays and Torrey here. Torrey's or Grays is right behind Torrey and just barely peeking over it. So the two highest peaks on the Continental Divide. Okay, there's St. Mary's again. There's Berthoud Pass. Eisenhower Tunnel, taking our tour around again. Oh, how'd that start over again? Huh. Okay, Vince, nice job. Okay. Keystone, the pull-off at Dillon Reservoir of I-70, I think, is a really nice place to look, especially when you get a gorgeous day like this day was, and this looking at grizzly and tories and grays from a different view than from what you see on the other side of Eisenhower Tunnel. And this valley here, behave. This valley is at Keystone, and a glacier stopped right there about Keystone, made it down there. And then out in the reservoir itself, there's some interesting things. So this is the view here of, this is the town of Keystone right down here. And, or the suburbs of Keystone. Here's the green arrow is pointing to the ski area, and you can see all the ice that came down from Loveland Pass and other places and ended up in Keystone. And there are really nice lateral moraines extending out from Keystone. This is one of the lateral moraines in the upper right there. And this is looking up where that ice is sourcing from, and you can see that all of this ice here, now this is Gray's Peak, Torrey's, Grizzly, Lenawi. This is the A Basin ski area. So a lot of ice coming from Loveland Pass and going down the Snake River, but a lot of ice coming from the side of Grizzly and Grays and Torrey, on both sides of Grays and Torrey, and the Continental Divide shown here in red. So all this ice is going down, and they join at the bottom and then flow through where Keystone is today and flow out and deposit that nice lateral moraine that you see out there. Oops. And then from this side of the mountains of the Continental Divide, these are flowing in and feeding that Clear Creek Glacier that we saw coming up I-70 to Eisenhower Tunnel. Grand Mesa is a really cool place, I think, and LIDAR has really enhanced our understanding of it. And if you want the definitive work on Grand Mesa, hopefully you can see this. This is a newly published book by Rex Cole, and is a great expose on the geology of Grand Mesa, as well as also has the older glacial geology that he's found, which is complicated. And I want to stick just with the Pinedale. There's the Colorado River up there at the upper left that's flowing down, that has exhumed a lot of material away from Grand Mesa in the time that it's been being eroded since the 10 million years ago that the volcanic rocks flowed out on top of it. Notice how flat it is up there on Grand Mesa. Just really amazing. And the reason it's flat is because that top is made up of these lava flows that are just stacked one on top of the other. There's one lava flow, another one, another one, another one, one right after the other. And there's very soft material, very erodible material underneath the lava flows, which is an important feature that we'll see in a little bit. And on top of Grand Mesa was an ice cap, just sitting up there on that flat area, and it flowed over the edges of the flat top and down a ways. So this is one of Rex's cross section of how, remember I said all this material underneath the volcanic cap is easily erodible. And as this erodes under, the caps will fall down and then rotate, and you get all of these rotated slump blocks in this area here. And so as we look out from the road heading up to Grand Mesa, we are looking out over these rotated slump blocks. So there's the Land's End way out at the point. And here is a rotated slump block similar to the cross section up above. Here's another one, here's another one, here's another one, here's another one, and here's another one. So those things have rotated down. And the same thing happens on the other. And both of them have created all of these areas of lakes. So now here's the LIDAR looking at the top. And here is the Pinedale moraine right here. You can see how lumpy it still is. Here's a Bull Lake recessional moraine. The actual moraine is out toward the point more, but this is a really nice example of a Bull Lake moraine compared to the features of a Pinedale moraine. And you notice that it goes right up to the edge, and this comes right up to the edge here. And actually it goes down in here, and then it comes back over here, and then it goes off this edge into here. And really the LiDAR has been helpful, extremely helpful in figuring out just what's going on there. So the little dashes outline the edge of the flat top. The big dashes outline the areas of these rotated fault blocks. And you notice that they're on both sides, all sides actually. So zooming in a little closer, you can see the Bull Lake recessional moraine back here and the Pinedale, Pinedale right here. Here's what the Bull Lake recessional moraine looks like on the ground. It's just mainly a rise. You'll see lots of boulders on it. There's ground moraine and boulders around below here. And the Pinedale terminal moraine is here. And when you look at that, you have these lumpy areas that when it rains, these things will fill up and fill little lakes in here, little round lakes that are pothole or kettle lakes. And the basalt itself has striations on it. These things are really subtle, and you have to have the right sun angle to really see them. And they tell us where the ice was flowing up on top. And so somebody's gone out there and mapped all of these directions of the flow of these from understanding these striations. The picture was taken on this county line knob right here. Okay, so you see that these are going out over the edge here. Here they're coming toward the moraine just like they should. And here they're going over the edge to the south. So as we look at this, so the ice seems to have been centered right here, the ice cap, and it flowed out in all these directions and flowed out to this point, flowed over the edges of the flat top into the lake. The reason I'm emphasizing that is because as we look at this, look at this area right here. You see all those lineations that are pointing off to the northwest? And we come up here and you can see all of these lineations in here that are pointing in a slightly different direction than the ones before. And there's some up here. So those are actually mega lineations from the ice moving out. So here the ice flowed down and deposited this moraine. And there's the outline of the moraine down in the landslid area. In this rough eroded topography here is where the glacier was moving over this and eroding this and flowing over the edge onto the area where the rotated blocks are. And notice that within that red area, you see all these lineations that are parallel to that blue area. The other thing that you notice is that the blocks here, rather than being sharp at the top, are rounded. As you get near the moraine, the end part where the glacier went, they become sharper. And over here, they're very sharp, but as you come in here, they're rounded. That's because the ice, the glacier was eroding the tops of those eroded blocks and rounding them off and striating them with those great large striations and grooves. Same thing, the ice was going here, and in this area, it was going a slightly different direction off of here. Here we have smooth topography. This area that you can see is not rough. And then as we get down here to the south in the lower right-hand corner, you can see we're coming off the edge of that block and we're going over the edge, and there are these lineations here showing us that we're going toward the south and eroding toward the south. So the smooth topography that we can see on the LiDAR is where the ice cap started. And as it moved out in all directions, it eroded the tops a bit. And as it flowed over the edge, it really eroded. So here are striations that you can walk out. There's a little trail to walk out to this, showing how the lineations are heading out into thin air and nothing there. Okay, another place, a lot of people have stopped here and seen this view before, looking out into the lake, and you look across the lake and you find this peninsula. It's called the Peninsula Recreation Area. But how many of you actually seen what that is? If we zoom in on this little area right here, we see that it's a Pinedale moraine stacked up against a Bull Lake moraine. And we looked at the LiDAR of this way back when we were talking about initially about Bull Lake and Pinedale moraines. So next time you pull off to take a break, take a re-look at the peninsula across the reservoir. And then, of course, there are all these little scattered islands that seem like they just, they're just random little islands out there. And why are they there? What are they about? May not have wondered about that, but here is the peninsula right over here with the Bull Lake and the Pinedale moraine. But if you notice, these scattered islands allegedly are not scattered. They're very organized. And the next picture, I think, shows that, or the one after this. So the ice that came out into where Dillon Reservoir is today basically stopped right here during Pinedale. And if you stop at the rest stop that, you just to pull off for the trucks, but you can pull off there too, you're actually on the Pinedale moraine, and you can just walk and go up on that a little bit. It takes you maybe 10 steps to get up there. So the ice started at Vail Pass and went down to Vail. There was an ice cap or an ice field actually at Vail Pass. It sent one arm down toward Vail Pass, and it sent the other arm down toward Copper. And then that arm, that glacier, joined with another one coming down from Fremont Pass, and they went through the Officer Gulch area that we looked at some features in there before, and came out into this area. And there was another source area for a glacier coming out to join that other large glacier that initiated at the ice fields at Fremont Pass and at Vail Pass. And they all ended up out here in Dillon Reservoir. And here I think you can see quite clearly that's a recessional moraine those islands are forming. Here's another recessional moraine and another recessional moraine. So these things aren't just scattered little islands out there at all. They have a very regular pattern that are reflecting the retreat of this glacier that advanced all the way out to here. So I hope, you get this view down at the sand dunes of the beautiful scenery. You look at the sand dunes and the beautiful scenery, but I hope that maybe now you'll take a look and you'll see that there's actually a wonderful little cirque up here above the sand dunes, and that you can begin to do that all over the state, and that your travels around the state will be much more. So I really appreciate you attending this, and I thank Kate and I thank the anonymous donor for letting it be free for you. And that's it. If you have any questions, or if you discover some cool things, let me know about it. I'd love to hear about it. Got time for a few quick questions.
This is Jennifer again. So it seems like the rotated slump blocks were very similar to the processes of the Secungan?
No, they're both responding to gravity. That's correct. So from that standpoint, That's correct. But it's really the erosion of the soft material under and eating back under the volcanic cap that causes it to just drop off, break off once it's undercut and rotate down the slope. So they're both gravitational processes, but the one is really a bulging outward. The other is from erosion and undercutting.
Okay, thank you.
Did you have a question, Larry?
Yeah, I had two questions, Vince. Basically, the first one is I probably missed it. In rock glaciers, is the ice residual from the Pleistocene, or is it modern or Holocene ice?
That, I think there's conflicting evidence on that, but Bob Anderson at CU has dated ice that he believes that the ice goes back not to the Pinedale, but maybe back 10,000 years. And certainly rock covers like that really form a wonderful thermal blanket that can preserve ice beneath. So, I mean, that's pretty well established. But I can't quite grasp a lot of this, and I think that there are some dates and hypotheses that I'm not sure are really well tested yet. But supposedly there is older ice under rock glaciers in Colorado.
Good. So my second question, Vince, is I hadn't appreciated that Grand Mesa had those moraines, striations, and glacier on top. It doesn't strike me to stretch our imagination very much to take that glacial information across to the northern uncompadre Unawib Canyon and even those canyons in Colorado National Monument. And yet people don't do that. Can you kind of put that together?
I would rather just stick with Grand Mesa.
Okay. Yeah, it gets
I'll stay out of a
complex.
lot more trouble that way.
Okay.
Well, there's a couple of questions on the chat. Let's see. Oh, Jennifer asked a question, but did you chime in and have your question answered?
It was answered in the lecture right after I asked it, so.
Oh, perfect. I love when that happens. And then Dee asked, were volcanoes before or after the glaciers?
Well, there was one volcano that was after glaciers, the Dotsero volcano that's just east of the Glenwood Canyon, and it was 4,000 years ago, and the glaciers were gone about 14,000 years ago. That's the only one that I'm aware of in Colorado that was after the ice ages. There's another one, there are some that are around, there's one that's about 250 or 300,000, that's fairly near Dotsero, and there are some that are about 600,000, which is getting back quite a ways. Still in the
Thanks,
place.
Vince.
Vince, Mary asked, where can I buy Rex Cole's book about Grand Mesa and who published it?
I don't know, is he on here? He was on last week. I got it from his daughter. I think she's publishing it. You can get it at the Visitor Center up on the Grand Mesa. The Visitor Center on the south side of the Mesa sells it, and this is saying Grand Mesa Geoscience Education. But if anybody wants to buy it, just email me and I'll send you the email of his daughter who is selling them.
Perfect. Well, that was it for chat. Vince, what about your book upcoming? Do you want to talk about it?
Well, it's being in its final review right now by the director of the Colorado Geological Survey, and hopefully it'll be out soon. When it does come out, it'll be available, as I understand it, free as a PDF, or you can purchase an 11 by 14 hard copy print on demand. I have no idea what the price will be of that or how to do it. But if people would like, I'd be glad to send out a notice when it's available.
Oh, that'd be great. Yes, please do. Vince, thank you so much. This was so interesting. I know other people may have questions, but I have to sign off now, and we so appreciate you doing this. It was really absolutely fascinating. And as I say, I'm going to have to add like another hour and a half to my hiking times from now on.
Good, good.
Really appreciate it. It was great. Thank you.
Thanks.
Key.
Appreciate that.
Well, I guess as Bugs Bunny put it. Wait, how does it go? Beep, 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 beep.
Yeah,
Beep, beep,
that's the
beep.
road. That's the road runner. You're too young to.
Oh, well,
those.
doesn't it? No, you go. Rah, rah, rah.
No, bugs go. Yeah, yeah.
You're thinking of Porky Pig.
Oh, I'm
All right.
sorry.
Time to move on. Thanks very much for your attendance. I appreciate it.
Thanks so much, everybody. Hope you have a wonderful rest of your day, and thank you to Vince. Bye-bye.